This is an introduction to acids and bases for first-year chemistry. We see here a sulfuric acid plant. Sulfuric acid production is one significant measure of a nation's economy. Why do we recognize acids so quickly when we encounter them? Well, hydrochloric acid is a principal constituent of stomach acid. And as a baby, we spit up the food that we eat, some kids a lot, and that gives us the sour acid taste very early in life. It's one of the 5 basic tongue responses. So it helps us to avert sour milk and bacteria, which are bad for us. The decomposition of sugars in the mouth will produce various acids, and this must be counteracted if enamel decay isn't to accelerate beyond what it normally would do. That's why we brush our teeth. Baking soda is often used as a dentifrice because it neutralizes the acid that the bacteria will produce. Common acids that you frequently find in foods are acetic acid and citric acid, of course, in citrus fruit, and lactic acid in milk products. Now, not in food, but in ant venom, you find formic acid, from the Latin word formica, which means ant. The mineral acids, which we do not find in foods, are sulfuric, nitric, hydrochloric, phosphoric, and many others. They're formed from the reaction of nonmetallic oxides in water. This is something you may have encountered earlier when you studied chemical reactions. Electrolytes, to review, are compounds that, if dissolved in water, form a conducting ionic solution. For example, any salt that has any solubility in water to that extent will be a strong electrolyte. That is, sodium chloride, ammonium nitrate, they're always 100% dissociated in water. All of the salts break up into ions, positive and negative. Now, you also know that acids and bases are electrolytes, but we will see that not all of them are strong electrolytes. Some are weak. The classes of acid, to review them, strong acids are strong electrolytes, and we ask you to memorize hydrochloric, sulfuric, and nitric with their formulas. They break up 100% in water. Weak acids are weak electrolytes, and most acids are weak acids. So all organic acids, hydrocyanic acid, hypochlorous acid that you find in swimming pools, acetic acid, of course, is the principal one that we study, and that is an organic acid. So what is the electrolyte in all acids besides the anion that they produce? Well, all of them have hydrogen, which can dissociate from the molecule of acid to form H+ aqueous. And bases are generally hydroxides formed from the reaction of metals or metallic oxides with water. You may recall sodium reacting with water to form sodium hydroxide. Calcium reacts with water, and calcium oxide reacts with water to form calcium hydroxide. Bases have a bitter taste. Please don't try it. Bases react with acids to form salts and water. Bases are electrolytes. The strong electrolytes, the ones that are highly soluble, strong bases are strong electrolytes, and those are the highly soluble bases. Potassium hydroxide, sodium hydroxide, the group 1 hydroxides. Barium hydroxide is also considered to be a strong base, although it's not real soluble in water. Ammonium hydroxide, that's what you use perhaps to clean windows, is a weak base. It doesn't break up 100% in water, and it is a weak electrolyte. So let's try completing and balancing some equations here. When you see them all, you can then turn off the video and come back and check your answers. Sulfur dioxide and water, ammonia and water, sodium and water, beryllium oxide and water, and dinitrogen pentoxide and water. Complete them, balance them, and then come back and check your work. There are your answers. SO2 produces sulfurous acid. Ammonia produces ammonium hydroxide. Sodium, you'll recall, reacts to form hydrogen and sodium hydroxide. And then, of course, metallic oxides give you the hydroxide of that metal, and non-metallic oxides give you an acid, in this case nitric acid. Pardon the following slides. If you already know these things, you can skip them. Binary acids, HX, where X is a nonmetal or a non-oxy anion, like hydrochloric acid. Hydroic acid, that's how you name them. HBr then is hydrobromic. HCN is hydrocyanic. It acts like a binary acid even though there are 3 atoms in it. And hydrosulfuric is H2S. HF is hydrofluoric acid, which is a weak acid, like hydrocyanic and hydrosulfuric. Hydrobromic, like HCl, is a strong acid. Oxyacids, the highest common oxidation state of the compound, the element that's going to be oxidized in the compound to make it, like sulfur or phosphorus. The highest common oxidation state gives you the ic acid. It corresponds to the 8 salt. So for instance, sulfuric acid, H2SO4, would be related to sodium sulfate. Nitric acid would be related to sodium nitrate. The next lowest oxidation state of the central atom gives you the us acid. It corresponds to the ite salt. So sulfurous acid would come from the sulfite ion. Nitrous acid comes from the nitrite ion. Your best bet is just to memorize the common ions and realize that when you take one oxygen off of an ic, you get an us acid. So here's another technique. Memorize sulfuric acid, H2SO4. So H2SeO4 is selenic acid. If you memorize HCl hydrochloric, you get HBr hydrobromic. For bases, remember that OH, the hydroxide ion, has a charge of -1. You need to couple the proper number of hydroxide ions with the metallic ion. And the group number on the table at the top, 1, 2, 3, and so forth, gives the charge on the ion. And typically we don't go past 4. So for instance, barium, you'll find that in the second group of the periodic table, the alkaline earths. Barium has a +2 charge. It'll get 2 hydroxides. Now, to finish off this video, we need to talk about water dissociation. Water is a very weak electrolyte, and ordinarily we consider it to be a non-conductor of electricity if it's pure water without any, say, carbon dioxide dissolved in it. So here's how water dissociates. The H2O breaks up into hydrogen ions that are in water solution and hydroxide ions. But that's not exactly accurate. We call it the self-ionization of water, so that the hydrogen ion is surrounded by water and the hydroxide ion is surrounded by water. The hydrogen ion in water is sometimes called the hydronium ion, H3O+. But we know from research that this is a fiction. There are always 5 to 8 water molecules surrounding any hydrogen ion. And we can show this with the Dickinson-Gray diagram here, that the hydrogen ion is oriented toward the negative end of the water molecules, and there are several of them surrounding each hydrogen ion, not just one. Let's watch the collision of 2 water molecules to form the hydronium ion and hydroxide. The collision gives you H3O+ and hydroxide, and that is one way of showing the self-ionization of water, or the dissociation of water. And this gives you a little animation to show you 2 water molecules striking and forming the hydronium ion on hydroxide. And remember The hydronium ion and hydroxide will be surrounded by water molecules once the self-ionization has occurred.